In the previous video, we created a server-side API for the contact form with basic email notification. Now, it's time to start saving all of our requests to a database. Furthermore, let's enable visitors to book calendar slots, ensuring that no slot can be booked more than once. For this, we will use a PostgreSQL database. In this video, we will add it to our infrastructure, figure out how to run migrations, and walk through some basic, typical interaction examples. Let's start by adding PostgreSQL into our infrastructure plan. Tactics remains the same. We are copying some existing module and tune the copy according to our needs. No public zone here, only internal network. And we probably need to manage whether the open ports for the database or not. The benefit of Terraform plan is the ability to generate random passwords for every environment. Docker resources to introduce are Docker image and Docker container. It will add Postgres to our internal network, and we are leaving ports and labels to be defined in locals outside of the resource. This is what connection string would be. This is the right place to define environment variables, and if you want to play with configuration, it can be provided here in the command line arguments. For the output of the module, we only need connection. Now we are referencing our PostgreSQL module in the application layer. And with the next step, we care about our server-side API for the contact form. It has connection URL on its input, and that connection will be mapped to environment variable. Checking that everything is correct and fixing errors. Our Terraform plan preview seems to look fine. And we can see it was launched successfully. To work with the database when its ports are secured, we need at least a few more things. The very minimal requirement is being able to jump to the shell of our database with one command, and the second requirement is to be able to store and run database migrations in order to have a continuous delivery. Now, I'm showing the way we are including bash scripts in our Terraform plan. This way, they are generated in a subfolder of our workspace. The scripts are simple enough. They will be just remapping our operations to be executed inside of our Docker network. The generated scripts should not be included under the Git tree. Here we have them in the bin folder. And this is how easily we can enter the database terminal now. For the database interaction, we will use SQLX library, and the part of it is a command line interface, which is convenient enough to use. SQLX migration add command will create a new SQL file with the timestamp to be our migration script. And as it was run inside a virtualized environment, we need to fix permissions first. It's time to define the table for the storage of the contacts. As calendar slot was introduced as a special string, there will be additional field called day that will store the index for the fastest query of all the slots of that day. Running the migration. And here we can see it was applied. Our new table was created. However, before coding, we need to help Rust compiler and syntax checker to have a connection to our database. It needs it because SQLX checks our static SQL queries at compile time. That forces us to put database URL environment into .env file on the root level of the project. But I'm on Linux, and there's the luxury of taking IP address of the running container, replacing the host in the database URL taken from the scripts we just deployed. If you are using Mac OS, then unfortunately you need to open database ports for your local workspace and use such credentials. The next thing we need before jumping to code is to prepare a writable folder where SQLX will cache precompiled queries. We are done with our Terraform plan and environment modifications, and finally ready to focus on coding. Now let's go to the protocol and add dependency of the database and adjust that we need it only in the case of the server-side compilation. Now we added the same dependency for the server crate to have a database connection pool in our prelude import. Database URL becomes our required variable to launch HTTP server. When we have PostgreSQL database connection pool passed, we are making it a part of shared application state for our endpoints. And the correct function of initialization is actually called connect. Okay, it's compiling. Let's add one more module to our protocol that is responsible for containing writers of the database here. Contact slot structure seems to miss transformation into the string to be stored in the database. That will be our function to write a new record in the database. Compile a check, that means SQL was written correctly. Slot is a special structure and requires some handling. Now, all we need is to reference that writer function in the HTTP endpoint before sending the email and handle its error with the server failure. Now, let's ensure database URL and other environment variables are set up in our terminal. Then we can just go cargo run server. Okay, server is healthy. Endpoint for submission seems to work. Now we are getting to the handling of the read queries. And we can do that in one more module called list, which will also be a significant growth point for our logic. But before jumping there, what we are missing in contact form entry structure is a definition of behavior that will allow to treat it as a database record, so-called from row trait. The most complex here is handling deserialization of the slot from string, handling all of its edge cases. Let's continue with the list module. The top level thing about it starts with two structures: contract form entry filter and contract form entry list, which basically mirror the logic of request and response. Into params instead of to schema explicitly tells us that it is expected to be passed using URL query parameters, and it will never be a JSON payload. And we obviously missed a few traits here. The only filtration we allow so far is filtering by day, but filter structure will also encapsulate how we expect results to be sorted, what is the limit and offset of the data. Sorting will define part of the SQL request. On the list, we can have custom debug implementation in order not to show all the results and use just number of rows in our logs. The construction of the list from the database can be declared as fetch function. Here, we have just a typical wrapper, and everything regarding SQL filtration actually goes to the apply function of the filter. We are just filtering by the day. Setting the limit. That's it for the list definition. But the actual contact form, we don't need the list of entries to be publicly available. What we need there is only the list of busy slots for the selected day. That would be enough to tell whether the slots are busy or not and will not expose anything private. So, in addition to contact form entry list, we are introducing contact form slots list. That's the structure that will be publicly exposed in our API, and it can be constructed from the contract form entry list by mapping slots and flattening the results. And it's a time to add a new endpoint. The same way, we define the endpoint in the Open API first, and then put our fetch function as a body with proper conversions and error handling. We will also include our endpoint and newly introduced types into Open API declaration. The key moment that just happened was a call of SQLX prepare command. That command had prepared cache in .SQLX folder that precompiled our queries, and now our application can be compiled without working connection to a database. Please make sure you've also added SQLX offline flag in your Docker file. That precompilation on writers module was a huge time saver for our delivery, but unfortunately it doesn't work for the dynamic query builder like we just introduced. So now you are watching me pathetically figuring out that migrations need to be done again and doing a few iterations of redeployment in order to add the spaces that were missed. Okay, fetching the list seems to work finally. It returns no slots, just like expected so far. Connection lost is the error message that our email server is not in place, but we are not focusing on it for now. The final part of this section is responding with the error if the slot is already booked. So, in the endpoint itself, let's reference the logic that will be defined in isBusy function. And to have a clear code, let's write the function to compare where the slots are intersecting. The function itself will be based on fetching the list filtered by the day of the slot. And after the data was fetched, iterate over each row and compare the intersection. That's it. There are just minor errors to fix. Let's add some debugging and launch with a cargo run server. Here our filter doesn't seem to work correctly. Well, day is a text string in the database, so we need to have a conversion from date. And we finally have what we expected in the list of busy slots. Okay, we're finally ready with the server-side APIs examples. Now, in the next series, we will learn how to do a client-side right on the same code base. So, jump to the next video.